Yeah, Nagraj, I think you can begin now.
I'll just share my screen. Tell me if you can see it. Can you see it?
Yes, yes, you can see.
Okay, yeah, let's start. Hello, everyone. I'm Nagraj and I am here to give a brief talk on the topic of observational techniques in astronomy. Before beginning, I would like to introduce myself. I'm Nagraj Vernekar. Uh, I'm a master degree student from KU Leuven, Belgium. Uh, I have uh, I have specialized in the topic of astronomy and astrophysics in my masters, with an interest in stellar evolution and stellar structures. Currently, I am a research assistant at Indian Institute of Astrophysics, working on massive star formation. Yeah, let's start now. So, what is observational astronomy? Astronomy is a wide field. It is further divided into three different subtopics, which is observational astronomy, theoretical astronomy, and computational astronomy. In observational astronomy, the astronomers try to study celestial objects like stars, galaxies, supernova by collecting the data from these objects using different instruments like telescopes, interferometers, and etc. And then look at that data in look at the observed data and interpret what might be going on in that star, uh, which is why we are getting the particular data that is observed. So uh, so this is the gist of the entire observational astronomy. uh, you might when someone puts it like this, it might seem that it is pretty straightforward, that you just take the data and you look at it and see what's happening. But like everything else, there is a lot of challenges that one has to face when you're trying to do something. The first challenge is the objects that you're trying to study are really, really far away. Like you know that the universe itself is so large, and it has billions and billions of galaxies, and each galaxies have billions of stars, and each of the distance between each of these stars is so large that it's beyond imagination. Here in the photo, you can see the galactic disk of the Milky Way. And you, just to try to realize how far these distances are, you can see that the center of the Milky Way, which is the supermassive black hole in the center, Sagittarius A, is around 26,000 light years. So light itself takes 26,000 years. If you want to put that in the units that we use in everyday life, it's 2.4 into 10 to the power of 17 kilometers. This we never come across such a large number in day-to-day life, but yeah, this is the distances that you're working with. And in this image, you can see a small speck of a blur kind of a image, and here, and this is actually the Andromeda galaxy, which is the closest galaxy to Milky Way. But even though it's the closest, it's still 2.5 million light years away. In kilometers, it's around 2.3 into 10 power 19 kilometers. That's like a quintillion kilometers, which is immensely large. But there is one good news, that Andromeda is coming closer to Milky Way. So in a few million years, you might even be able to visit it if we are alive. The second difficulty comes because of the distance itself. Uh, let's take an example of a star. A star radiates energy, and it radiates in all directions equally. But because, so when the distances from the
That's
star,
exactly what.
sorry, okay. So as the distance from the star increases, the total flux that you observe from Earth is a very small fraction of the lumina of the flux that the star actually emitted. The all the other percentage of the flux is just goes away in every single direction. So due to these immense distances, the flux that you observe is very, very small. And this is so when you're observing something like other galaxies, the light is the number of photons that you observe is so short that you need to take very long exposures, and that kind of adds into the difficulty of trying to analyze certain objects. The third difficulty is very close to us. It's the Earth's atmosphere. So Earth's atmosphere, even though it's very good for humans, it gives us protection, it gives us oxygen and everything. It is it makes an astronomer's life very difficult because Earth's atmosphere, it's not static. So it's not same all the time. Earth's atmosphere is very dynamic, that it changes. There is like wind flowing, so the density of the layers of the atmosphere changes constantly and very fast. So when you try to observe, so you have a ground-based telescope and you try to observe the light from the star, the light actually it shifts due to the difference in the atmosphere. You could have seen it from your naked eye itself, that stars twinkle. You can see stars twinkling in the sky. That's not because the star is doing something, but it's because the Earth's atmosphere is very turbulent. And when you try to observe when you observe something in the turbulence of the Earth's atmosphere, then this is the image that you get. It's You can just see the blurriness in the image, and you can just see blobs of light everywhere. This can still be used to study certain phenomena, but there's a limit to what you can do with this image. And with the current day level of research, uh, this is not enough. This type of resolution is not enough. This type of sharpness in the image. So they have come up with an ingenious solution which is called adaptive optics, where they artificially first create an artificial star using lasers. As you can see, this is the very large telescope from European Space Observatory, Southern Observatory. So you can see the lasers shooting up, and it creates a artificial star in the field of view. And then they look at that star. It gives an idea of what the atmosphere is doing, and then they correct that disturbance using uh, a flexible mirror, where you can change the curvature of the mirror based on your inputs. And this is done tremendously fast because the atmosphere changes so quickly. This whole technology is called adaptive optics, and here you can see a real life example of how adaptive optics increases the resolution of a telescope. You can see that the blobs just become really good stars, like they're really finite. Coming to the level of improvement that adaptive optics brings, you can see that here it's the VLT, which is the same telescope. You can see the image above, which is the very large telescope. The resolution of VLT is comparable to the resolution of Hubble, which is $1 billion space telescope. So using this technology, you can build much larger ground-based telescopes, which have a resolution better than the space telescopes, because launching space telescopes is a tremendous task and also takes in a lot of money. The fourth challenge is the light pollution. As you know that if you live in a city anywhere in India, you barely see a few couple of stars in the sky. But in reality, this is what you need to see. So if there was no light pollution, this is what you would have seen every day, like every night. But because there is so much light usage in the cities, it illuminates the sky, which then reduces the visibility of telescopes around the world. So there is not really any way to correct light pollution. You can use filters, but again, that will increase the exposure times of your observations, which is not a good solution. So the only solution that currently is used is to build all the telescopes away from cities and everything like that. Currently, there are handful of hotspots around the world where telescopes are built because of their pristine conditions. One of them in India, it's Ladakh. So there are few telescopes in Ladakh where people observe from. There is one in Mauna Kea, that is USA. And the biggest of all is the Atacama Desert in Chile, where there are like one of the world's biggest telescopes situated, like the 40-meter extremely large telescope, the giant Magellanic telescope, and also the ALMA radio telescope. So I have addressed the third and the fourth issue of how astronomers try to solve it, but they're still the first two issues, that the distances and the brightnesses. So how do we actually study these such distant objects? There are a few techniques that we use. Each of these techniques gives a different each of these techniques probes a different phenomenon. So there are like 5 different techniques here. So first one is photometry. Photometry is the simplest one. I feel that it's the simplest one, where you just monitor the brightness of the star that you're looking at. So you just constantly take observations and see how the brightness of the star changes. Here is an example of an eclipsing system. So there are two stars which go around and they eclipse just like the sun and moon does, sun, earth, and moon does with each other. So when the eclipses occur, you can see that there's a dip in the light curve, and these are periodic, even though they don't seem periodic. They are. This is because this is an eccentric orbit. But yeah, this happens in a periodic fashion, and you can, by just looking at it, you know that there is more than one star in that system. So this is quite useful, and you can also study. So you can see here there is a lot of variation. So there's up down, up down, up down. This is the pulsations in the star. So the star is a way, like it the radius increases and decreases in time, with respect to time, and that causes certain changes. Why this occurs? It's some internal mechanism, which is a complicated subject which we are not going into. The second technique is spectroscopy. So spectroscopy is a technique where you take the light from the star and then you split it into all the constituent colors. So you split the light that you get and into a spectrum. So this is what a usual spectrum of a star looks like. You can see that there is like the Vib Goyard that you see, the rainbow thing. So there's red, there's yellow, there's green, there's blue. But along with those colors, you can also see some black lines in between. So there are many black lines, like a lot of them. So what are these? These are actually, so it's not a continuous spectrum. This is because star is made up of many different elements. Like the most abundant are hydrogen and helium. So when the light travels in the star, these elements absorb certain frequencies of light, and when they absorb the light, it no more reaches you, right? So at those particular frequencies, you don't get any light, and that is represented by the black color here. You can actually study these. So these are called spectral lines. Each of these dark lines are called spectral lines, and you can study these spectral lines to actually know what kind of composition the star has, and if there is something going on in the star. And it's an extremely it's widely used in the astronomy space. The third one is interferometry. Interferometry is a technique where you um, use multiple telescopes to increase your resolution. So the resolution is what is resolution? What do I mean by resolution? So you have two very close stars. When you look through a small telescope, those two stars will look just like one star because they're so close by. You cannot really differentiate between them. The light just merges into one. But when you use a larger telescope, the resolution increases. So you can see the two stars separated. So you know that there are two stars. But again, there is a limit to how big a telescope can be. You cannot build a 1 kilometer 1 kilometer diameter telescope, because the cost and the engineering that goes behind building such a gigantic telescope is just too much to ever even consider building such a thing. So what is the next best thing? We use interferometry. Interferometry is where you use multiple smaller telescopes. Again, this is the image of VLT, which has four 8-meter telescopes. And so there is some separation between them. So this telescope and this telescope, there's a separation. and they observe the same star simultaneously. And then when the data is merged together, you get a resolution. You achieve a resolution of a telescope which has the diameter of the baseline. So it's an extremely useful and a cost-effective way of increasing your resolution. If you have ever heard of Event Horizon Telescope, which was used to image the black hole in M44. So they used multiple telescopes around the world, including one in Antarctica, to to form a virtual telescope which was as big as the Earth itself. So that's a gigantic telescope with a resolution far bigger than any other single telescopes available. And they were able to actually image the black hole for the first time ever, which was a miraculous task. Uh, the two other types of technique is gravitational wave detection. Uh, Black holes are remnants of dead stars where the gravitation is so large that even light cannot escape from them. And because light cannot escape, there are no ways of directly imaging a black hole because no light comes out. So gravitational wave is a indirect technique of observing these objects. So what gravitation is? So when there is a binary of two black holes, so they are revolving around each other, they eventually lose their energy and they come closer, and then they go into a spiral and then eventually merge. But this phenomenon is so energetic that they actually deform the space-time curvature. So they form waves in the in the space-time curvature, which then propagates in all directions. So when it hits Earth, we can now, at least now, we can measure this small differences in the space-time curvature, and then we can estimate the masses of the black holes that merged into one single black hole. Messenger particles are the third topic, which I will cover later. So in general, all of these, majority of these techniques use one common thing, that is light, except for the gravitational wave and the messenger particles. All the other three techniques, they use light from the objects. So light is a very important uh, topic in astronomy. Light itself is nothing but an electromagnetic radiation, uh, which has a range. So there is not just one type of radiation. There's a spectrum, and it goes from very high energy radiations to very low energy radiations. This whole spectrum is divided into a few parts, which is like gamma rays, X-rays, ultraviolet, visible, microwave, and radio wave. So you can see the the particular order, as well as the frequencies of these, the wavelengths of these radiations. Uh, and Astronomers use all of these different types of radiations to actually observe different objects. Here is an example of Whirlpool galaxy, which is a galaxy that you can actually see in a naked eye if you go to a darker sky. So you can see that uh, different waves, like different type of electromagnetic radiation, they probe different temperatures. Like, because gamma rays is so energetic, they are emitted from regions which are very, very hot. So like so here you can see that X-rays itself, X-rays are emitted from regions which are like 10 million Kelvin, like that's the temperature range where it is emitted. Whereas like radio waves, because they are very low energy radiations, they are emitted from anything that's like above, like around 600 Kelvin. So as you go across the spectrum, you kind of probe different sections or different phenomena occurring in the same object. And this is called multi-wavelength astronomy. And it is again very useful to see what is happening, because like if you take an example of a galaxy, there are many things. in the center of galaxy, there can be a supermassive black hole that is emitting gamma rays and all kind of higher radiations. But as you go away from the center, there can be star forming regions where stars are formed, where the uh, molecular clouds kind of come together and form stars. These are less hot regions, and they do not emit gamma rays or X-rays. So you need something else to look at these and study these stars, where you use like optical or infrared radiations. Radio would be again, it would again probe regions where there are cold gases like interstellar medium, to actually study how much mass does uh, the galaxy handle, etc., like that. So it's important to know all of these all of these different radiations and what they do. So let's just go one by one in order from the highest radiation to the lowest. So first, let's start with gamma rays. So gamma rays are again very energetic radiations, and they have a very short wavelength. So like a very short. The energies of gamma rays can go up to tera electron volt, and these are ionizing radiations, so it's very harmful to humans as well. So how do we detect gamma rays? Gamma rays, even though it's an electromagnetic radiation, it does not behave like a normal visible region radiation. Because of its very high energy and very short wavelength, you cannot reflect gamma rays through a mirror. They'll just pass through. So you cannot use a normal telescope to observe something like gamma rays. So what do? There are two different mechanisms that is used. One is used for the ground-based observations, and another is for the space telescopes. The ground-based observations use something known as Cherenkov shower or Cherenkov light. So when a gamma ray, a very high energy gamma ray comes in, it first because it first interacts with the atoms in the atmosphere, and then when it interacts with the atoms, it causes it to ionize, and then it goes on, and a shower occurs because they hit many different atoms of electron. You can see here that the red thing is known as the Cherenkov light, and this is detected by the telescopes that are placed on the ground. So here is an example of a high energy gamma ray telescope. So there are many. So there are many telescopes you can see here in the picture. There are 4. The reason you need so many telescopes and not just one is because you need because of the scarcity of gamma rays that is coming towards Earth. You need to cover a very large area to have a significant observation. So you need multiple telescopes. Coming to the space telescope, there is one space telescope that does gamma ray observations. They cannot, again, because of space constraints, they cannot, have a telescope which is like 100 meters wide. So what they do is they use something called as scintillators. Scintillators are devices where when a gamma ray comes and hits, electron is when a gamma ray comes and hits, there is a light emitted because of the energetic atom coming down to the ground state, and this light is detected by the detector. So through this mechanism, I'm sorry, but there is someone is not muted. Hello. Yeah. Okay. So how scintillators work is a gamma ray comes and hits the one part of the scintillator where the atoms absorb the gamma rays and then get energized, but then they quickly come down to ground state by emitting light, and then this light is goes through a photomultiplier, and then it's sent to the detector. So through this mechanism, they can detect gamma rays. and there is one telescope which does this from NASA. So what are the sources of gamma rays? Because gamma rays are very energetic radiations, they are emitted by one of the most violent phenomenons to occur in the universe, such as AGNs, which is active galactic nuclei. This is nothing but the black hole in the center of different galaxies. The black hole, there's a disk around the black hole which is feeding the black hole, but then because of certain phenomena like Eddington luminosity, there's a jet coming out of the black hole, and this jet is very very energetic. So that's where gamma rays are emitted. The other places where they're emitted is blazars or neutrons and supernovas. Supernovas are the remnant of a dead star. Neutrons and sorry, that's actually a neutron star. So a neutron star is again the it's so when a star dies, when a massive star dies, it becomes a neutron star. It's a very compact star. Next is X-rays. X-rays are still high energy radiations, but they're not as energetic as gamma rays, but they're still energetic enough to be harmful to humans. You might have taken X-rays sometime, X-ray scan sometime in your lifetime. Uh, but small doses are fine, but they're still harmful. So doctors always recommend you not to take too many X-rays because they kind of uh, damage your tissues. They are again short wavelength. They are shorter than UV rays and longer than gamma rays. Similar to gamma rays, these X-rays are also very difficult to focus. You cannot just use a mirror and then reflect the gamma rays like traditionally as you do with visible light. So what you do is, so there is one space telescope called Chandra, which is which has done a lot of useful observations. So you can see that there's a long tube in Chandra. So this is the inlet, and then there's a long tube, and then there is a detector. So the reason for this long tube is because you cannot directly reflect the light and then focus it to a point. What they do is they use something called as internal reflection, where they bring the light in. The mirror is placed such that the light has a very shallow angle, shallow incident angle, and then it gets internally reflected. So complete reflection. And then they do this multiple times to bring the light to focus. So so here it's a simplest explanation, but in the telescope there are many concentric mirrors placed in like circles, and there are a lot of them so that a lot of light can be focused into a point. The reason for it being a space telescope and there are no ground-based X-ray observatories is because Earth's atmosphere absorbs all the X-rays and does not allow anything to come in, and therefore you have to go into space and you cannot just do it from ground. The same thing holds true for gamma rays as well. Very few gamma rays can sometimes reach the Earth. The next in the list is UV rays. UV rays are nothing but ultraviolet radiation. You would have heard it that it's bad for your skin. You can get skin burn because sun emits a lot of ultraviolet radiation. This is a radiation between 10 and 320 nanometers. So that's the wavelength range of ultraviolet. Ultraviolet again. So even though some part of ultraviolet can reach the surface, a large portion of ultraviolet is blocked by Earth. That's the ozone layer, as everyone has studied before. The ozone layer, the ozone molecules absorb the ultraviolet radiation. Therefore, a very small portion reaches the Earth's surface. Again, so this is the reason you have to go to space. One So there is one particular important satellite that does these observations, which is AstroSat. So this is an Indian space satellite that was launched in 2015, I think. So so India built and launched it, has their first ever satellite as a space telescope and it's a multi-wavelength telescope, so that's something to be happy about. So this does ultraviolet. It absorbs ultraviolet sources. So some of these sources again can be AGNs, which is active galactic nuclei. Sun's corona being very hot, it also emits a lot of ultraviolet radiations, which again you feel in Earth. Certain white dwarfs, so white dwarfs have, because of their immense temperature of around 20,000 Kelvin, they emit strongly in ultraviolet. And this is also how they are detected, because normal stars emit majorly in visible light. Coming to infrared radiation, I have skipped visible because I'll just talk about it at the end. Let's come to infrared radiations. Infrared radiations, as the name suggests, it is after red. So after the visible light comes infrared radiations. Infrared radiation is nothing but the heat that you feel, like when you switch on a bulb, like the old filament bulb, then you can feel the heat coming out of that bulb. So that's because of the infrared radiation, and everything that has temperature will emit infrared radiation, even humans. This radiation has a temperature between 0.7 and 300 micrometers. uh, and yeah, so infrared again is observed from space, because there is so many infrared sources on Earth that it would be very difficult. So there'll be a lot of contamination, and it would be very difficult to actually do any meaningful observations. One of the best example for infrared observatories is the recently launched James Webb, which you might know. This is the most anticipated telescope to ever launch. It was in development from past 25 years, and it will be the best telescope ever built, with the best resolution and the best light gathering capacity. So this is the image of the telescope. Currently, it's in calibration phase. So 2-3 months from now, the scientific data will start pouring out, which is very exciting for all astronomers around the world. Some of the sources of IR radiations is sun, as you know, and exoplanets, because they get heated up from the star, the close by star. They also emit IR radiations, and that is how James Webb wants to detect these planets along with the transit method as well. Other sources are like, again, star forming regions, which are like cooler, so they emit IR radiations. They cannot emit like UV or anything. And populations 3 stars. Population 3 stars are special because these are the stars. So the stars that were formed early in the early universe, very close to Big Bang, these are called as population 3 stars. So the reason we will observe these stars in IR radiation is because they are so far away from us, that is like 13 billion light years, that the light that they emit, even though if it is in UV or X-rays, due to uh, uh, due to Doppler shift, due to redshift, the light would eventually come to the IR region. And again, James Webb wants to do this particular observations of IR radiation and check if there are any population 3 stars present. The next one is microwaves. Microwaves are this in my opinion, this is one of the most interesting discoveries that was made in this century. Uh, because like microwaves is what was used to observe the CMB, which is cosmic microwave background. Uh, so the microwave radiation has a wavelength range of 1 millimeter to 1 meter. So they're significantly longer wavelength radiations. So the energies associated are also very small. The reason CMB is so interesting is because this is literally the signature of the early universe. So the early stages of universe, it had some temperature and then it started cooling off, but the CMB is still present and you can actually observe it. So this is the telescope called Planck that observed the Planck telescope that observed the CMB, which is given below. You can see that. So it showed that the CMB had an anisotropy. So there's like it's not a smooth thing, so there is many differences, and it is interesting to know why there is difference. um, and also CMB was used to measure the age of the universe, also the Hubble's constant, and probe the dark matter, which is again a very mysterious topic for now. So microwaves have been useful in studying more about the early stages of the universe, and also estimating the age of the universe. The last and the least energetic uh, radiations are the radio waves. These are waves which have wavelength longer than 1 centimeter. And again, because they have such long wavelengths, they are very low energy radiations. Uh, Earth is very transparent to radio waves, so majority of the observations are done by ground-based telescopes. Here you can see that here you can see a photo of ALMA. ALMA is a again it uses interferometry technique, so there are like many different many antennas that observe the radiations, and then the data is clumped together. Uh, this radiation is especially important because these radiations are emitted from sources like pulsars. Like the pulsars are nothing but neutron stars with a jet coming out from it. Like AGNs, again, active galactic nuclei, the black hole in the center of galaxies. The Sagittarius A, which is the supermassive black hole in the center of Milky Way. So even though even though radio waves is one of the weakest weakest electromagnetic radiation in terms of energy, it still helps in probing one of the most violent events in the universe. So this is extremely fascinating that something so weak can actually probe so energetic events. At least I was surprised when I knew this for the first time. Here is a radio image of the Sagittarius A star, so center of Milky Way, and in the arrow it shows it's showing you, so you can see a cloud kind of a thing, that is the supernova remnant of a star that went boom in the recent past. Yeah. So at the last one is visible light. Visible light, as you know, is the region between the blue light and the red light, or the violet light and the red light, and it has a wavelength of 3,800 angstroms to 7,500 angstroms. This is the only light that us as humans can see. We cannot see the other radiations. And Yeah, so this is why. So this is where a lot of astronomy happens, because again you can build telescopes on land and you can go to space. Some of the examples are some of the examples of space telescopes is the Hubble, which is the iconic image here. It has done a very remarkable contribution to the field of astronomy, especially you might have known the deep field image, which kind of gave us an idea of how large the universe is. Some of these are some examples of ground based telescopes. The one on the extreme right is the LSST, which is a survey telescope currently being built. So this will survey the entire sky in like 10 days, so it will keep doing it for a long period of time. So it will help in finding a lot of asteroids and many different kind of changes in the universe. As a matter of fact, this has the largest camera ever built for any purpose. On the left is the extremely large telescope from European Space Southern Observatory. This is being built in Chile, Atacama Desert, and it has a primary mirror of 40 meters, which will be the largest mirror ever built. And so this telescope will have a really good resolution to do a lot of science. So yeah, let's just go in depth of the different techniques that I mentioned. So first, let's start with photometry. As explained, photometry is just a time series, and you measure the brightness of the system. And I also showed you an example of uh, of the eclipsing system that I showed. Uh, Photometry can be used to estimate the temperature of the star. This cannot be directly done through the time series. Instead, you use something called as SED, which is a spectral energy distribution. So it kind of gives you an idea where the highest emission is in the wavelength region, and through that you can kind of estimate what star you are dealing with. It helps in studying eclipsing systems. As the example showed, I'll show you why. Why? Here is a video from ESO. So you can see that the two stars are eclipsing each other, and then here is the light curve that you will get. So this is the theoretical, but yeah, this is what you would initially find. So when it eclipses, there is a dip in light curve, and when the other star comes in front, the eclipse depth changes. So by studying these eclipse depths and the difference between the two eclipses, you can find many parameters like how massive the star, what is the radius of the two stars, what are the masses of the two stars, what are the temperatures of the stars, and many more things like that, which is extremely useful in categorizing these systems. The other uses of of photometry would be something called as astroseismology. Astroseismology is a field where we study the star quakes. So like earthquakes, even stars have quakes in them where they kind of move, the surface moves. Here is an example of like two examples. So these are different kind of motions. You have a lot of different kind of motions in a star. The first one is the simplest one, where just the star increases, the radius increases and then decreases and increases and decreases. This happens periodically. And the second one is quite a complicated motion. The blue regions indicate the surface which is towards you. So it's like it's coming away, like it's coming towards you, and the red region indicate the ones that are going inside. So some regions are bulging outside, whereas some regions are bulging inside, and this happens again periodically. Uh, the reason for these things to occur is again certain phenomena happening inside the star, certain instabilities. Um, you can, if you want, you can just go through astroseismology and you'll find a lot of material if you're interested. And so this kind of variation in the star uh, has a effect on the brightness that you see in the light curve. So this is an example light curve of the same eclipsing system. But like if you remove the eclipses in between and you just concentrate on the out of eclipse region, you can see that there is a lot of variation in the light curve. It keeps going up and down, up and down, up and down. And like it might seem that they are just random, but these are actually a lot of periodic variations having a constructive interference with each other and then forming these variations. You can study these variations and then kind of analyze what the star is doing, and also probe the interior of the star, including the core of the star. That is why astroseismology is such a useful tool, because you cannot see the core of the star directly, so you cannot see inside the star directly. So astroseismology gives you an indirect way of studying the interior of the stars. Again, SCD has explained, kind of gives you the temperature of the stars, the temperature of the star, and you kind of know what kind of system you're dealing with. Coming to spectroscopy again, you split the light into constituent colors and then you study the spectral lines to see. So how do you split? So this is a kind of representation of a spectrograph, of a very simple spectrograph. Uh, so there's a slit through which the light comes in. So there's a telescope and then the light comes in through the slit, and then it's reflected onto something called as a diffraction grating. So diffraction grating is kind of an instrument that is used to split the light. So you can see that here it is represented that the white light is split into its constituent colors, and then the photo detector just takes in those different colors, and then it gives you the spectrum. The one that I showed before was a 2D spectrum, and then you can convert that into 1D, which gives you a line plot. And you can see there are dips. So these dips are the black lines that you see in the spectrum earlier. So you can see that there are a lot of dips. All of these are spectral lines which are formed due to absorption of light from different elements. You can study these in detail to know what kind of what kind of chemical compounds are in the star. The other use is to you can also study the motion of binary systems. So as explained, binary systems, there are two stars moving around each other, so they keep going in a circle or an elliptical orbit. But this motion, because when they are going around one star, from your perspective from Earth, one star is going away from you while the other star is coming towards you, and this motion causes something called as redshift and blue shift. So certain wavelengths of the star going away from you is like redshifted, whereas the light of the star coming towards you is blue shifted very slightly. So you can measure this. Here you can see an example of a star that's doing that. You can see that in some epochs there's just one dip, whereas in other epochs there are two dips. This is actually the same spectral line, but because these spectrums are observed in different point of time, the blue shift and red shift can be seen here. You can measure this using something called as a Gaussian fitting technique. Here you can see that I have fitted two Gaussians into the same spectral line, and I can measure the relative change in the wavelength and then calculate the velocity of the components. And here you can see the radial velocity of the two components. The blue one is the secondary, and the blue one is the primary, and the red one is the second. So you can see that there is a motion, like they reach a certain speed and then they come back. So that is the you can use this to study a lot more about the system itself. Coming to gravitational waves, as mentioned, gravitational waves are nothing but ripples in the space-time curvature. Here is a representation of what. So here they are showing two neutron stars going around, but this also holds true for black holes. So when they go around, they form these ripples, and these ripples travel across the universe. And when they come to Earth, you can detect it. But because these ripples are very, very, very small, the magnitude that you are dealing with is extremely small. So you need a very, very accurate detection technique. So there are three observatories on currently working, called LIGO and Virgo. So there are two LIGO at Hanford and Livingston, and one more in Italy. It's called Virgo. LIGO stands for Light Interferometer Gravitational Wave Observatory. So this is an image. This is the observatory. You can see that there are two arms which are perpendicular to each other. Each of these arms is 4 kilometers long. So what it does is, again, it uses interferometry technique. So there is light that goes in one arm and then is reflected back into this station, and same happens in the other arm also. But when they come down, they interfere with each other, either constructively or destructively. But when these ripples come to Earth, the circumference of the shape of the Earth also changes, because the space-time curvature itself is changing, and this change in the curvature itself will change the interference that's happening. So you will kind of get a signal where you can see that there is small and then there's a large changes in this interference of the light in the two arms. So you can do this and then see if you have actually detected a wave. Again, this is a very simplified version. The actual thing that takes place is much more complicated, because the changes are so extremely small that they have to take everything into consideration. Even like a man walking near these tubes can affect the results. So yeah, it has to be extremely sensitive. Using this technique, you can probe the masses of black holes and neutron stars, which is a very useful technique. And also So also in the early universe, there is a concept called cosmic inflation, where we think that universe expanded very rapidly in a very short period of time. So if that took place, then there should be gravitation waves originating from then, and we should be able to detect it now. But yeah, that is what astronomers are working towards currently. Coming to messenger particles, this is the last technique that we are going to discuss. Messenger particles are nothing but, so as the name suggests, these are particles which bring information to us. There are two important messenger particles. One is the cosmic rays and another is the neutrinos. Cosmic rays are nothing but high energy protons or alpha particles. Alpha particles is nothing but the nucleus of a helium atom. So these are very high energies. The energies can go from 1 giga electron volt to 1 exa electron volt, which is tremendously high. So when they come and when they hit Earth again, just like gamma rays, because of their high energy, they form cascade of showers, which is in this case it's called air shower, where they hit many different particles and then they form a shower kind of a thing. You can detect this shower. Just like you did for gamma rays, and you can estimate where it came from and all these. Some sources of cosmic rays are the sun itself, supernova remnants, and certain uh, energetic events like AGNs. The second one is neutrinos. Neutrinos are fundamental particles which so they are so light that the rest mass is almost considered to be zero, and because of this they also have a very weak interaction with matter, so they rarely interact with matter, which makes it that much more difficult to actually observe this. So how do we observe neutrinos? You can see an example of a Japanese observatory called Super Kamiokande. I'm sorry if I didn't pronounce it right. So this is a kind of a tub. This is a tube kind of a region where it is filled. So you can see the extreme size of this tube, right? These are humans standing here, and then this is like the size. So they fill this tube with like ultra pure water, and then these golden things around are like photo detectors. So they detect even the slightest change. So when a neutrino comes, because of its speed, it kind of it gives out a certain light, and then these photo detectors can detect that light and they can estimate how many observations are made. Even though such a big facility is available, the number of neutrons detected are very very small because they interact so less. uh, yeah, so again these are formed again in the supernova and sun, and these kind of give you an estimation uh, of what's happening in the early universe as well, because even Big Bang would have produced some neutrinos. So that was a brief session about different techniques that is used. Someone can either use one technique to do some research, but usually in majority of cases, astronomers use multiple of these techniques in together to kind of have a really good results at the end, which is useful. I hope this kind of gives you an overview of what observational astronomy is like, and hopefully it kind of encourages you to pursue this stream. Yeah, thank you. That was my presentation. If anyone has questions or anything, if you want to ask, then you can just ask right now. I don't think there's any questions. Hello, someone there, or am I just talking to myself?
Yeah, no questions such as, but thank you. It was.
Hey Nagraj.
Hello.
Yeah. So thank you very much, Nagraj, for this very wonderful session. It was very nice. And does anyone have any questions, guys? It's the right time to ask questions. You can unmute and ask. Mm, okay, so what we'll do is, I think I shared the link of our community, like Telegram and Discord. Join, and if there's any questions, you can post there, and I think Nagraj will be able to answer them.
Yeah, sure.
Yeah. So yeah, sure. You can ask in the Telegram group or in the Discord server. Okay, then. Thank you very much, guys, for joining, and have a wonderful Sunday evening.
Thank you. Thank you.